Alright guys, so in this video what I'm going to be discussing is polar and nonpolar bonds and polar and nonpolar molecules. So what I'm going to do right now is review polar and nonpolar bonds. And we've already gone over this in class, and remember the key thing about this is when we're talking about polar bonds and nonpolar bonds, we are talking about covalent bonding, the sharing of electrons. We're not talking about ionic bonding where electrons are going to be donated, right, between a metal and a nonmetal. Instead, what we're talking about is the sharing of electrons between two nonmetals. Okay, so just to keep straight in your head that polar and nonpolar, whenever we're talking about those two terms, we're talking about covalent bonding. Alright, cool. Okay, when we have polar bonds, this should be review. You are still sharing your electrons, but you're sharing them unequally. So share electrons unequally. Alright? However, with nonpolar bonds, the elements share their electrons equally. Okay, so in class I had a short demo for this, but in order to demonstrate polar and nonpolar bonds, I have a short demo for you. I hope you enjoy. Nonpolar bonding. Okay, so Toby's going to take this. Toby's going to grab this. Alright, grab it. Okay. Alright guys, and if we pull with equal force, this is nonpolar bonding because we're pulling with equal force right now. Alright, so this knot, which is our electrons, are equally between us. Alright, now he's just cheating. Alright, however, if I pull with greater force and bring it closer towards me, the knot closer towards me, it is now going to be polar bonding. Alright, because I'm more electronegative than Toby. Now what we're going to be talking about is polar and nonpolar molecules, okay? So this is going to be similar to talking about polar and nonpolar bonds, but it's slightly different because we're talking about the whole molecule now, not just the individual bonds. Alright? So when we're talking about polar molecules, what we have is that one end of your molecule is going to be slightly negative. So I'm going to write this. I'm going to define it, and then I'll show you an example. So one end of your molecule is slightly negative. Okay? Meaning there isn't a perfect sharing of electrons, alright? There isn't going to be a perfect balance. And in order to show this, I'm going to show you a couple of different of these models. Okay, the first one that I'm going to show you for a polar molecule is going to be this one. All right. Notice this is also what I showed for a polar bond, right? So, for example, let's say this smaller atom is going to be more electronegative, so it's going to be pulling the electrons more towards itself. Alright, this would also be a polar molecule. Alright, because one end, this end is going to be slightly negative because the electrons are not dead in the center like they should be if they were to be shared equally. Instead, they're going to be more towards this atom side. And so as a result, what's going to happen is we're going to say that this atom is slightly negative in charge. Alright, it doesn't have a full negative charge, but it's slightly negative because the electrons are more towards this end than towards the black. Alright, so an interesting fact, as soon as you have a polar bond, okay, like this, where it's linear, it's automatically going to be a polar molecule, which makes sense and it makes it pretty easy and nice and simple. Alright? Well, let's look really quickly. I'm going to define for you nonpolar molecules, and let's see how it gets slightly more complicated. Okay? Well, if you have a nonpolar molecule, what happens is that your bond polarities cancel. Your bond polarities cancel. Okay? So for example, if you have this again, right, you guys would agree that this is a polar bond as a result of the fact that these are two different elements. Alright, this one's going to be pulling with greater strength, and therefore it's going to have a slightly negative charge because the electrons are going to be more towards it than they are towards the black atom. Alright, so this bond is slightly negative, but then let's say we take it, okay, and we take that bond and we look at it in the context of a tetrahedral as a molecule. Okay, I've just kind of stepped it up one game. That was the one bond. Here's one bond. Here's the entire molecule. If you think about it, imagine each of these yellow atoms pulling electrons, and the way I'm going to represent it, imagine it's just like Toby pulling the rope, right? And so here's me. I'm standing right here. Okay, I'm that dot. And then the other dots, I have 4 dots for this because I have a tetrahedral, so I'm going to have 1, 2, 3, 4. So there are going to be 4 different Tobys. Okay, and the force that they're going to exert, those Tobys, oh, there are 4 of them, oh my, okay, are going to be represented by these arrows. So this force, okay, Toby is pulling the rope towards, this Toby's pulling the rope that way. And so if this were the only bond, alright, then yeah, absolutely, I would be forced to move in that direction. However, there are 3 other Tobys. 1 Toby here, 1 Toby here, and 1 Toby here. So if you notice, this force, this pulling down and slightly to the left, is going to be offset by this one pulling down and slightly to the right, and this one pulling up. And so what happens as a result is I would not move at all because all of these forces cancel each other out. And that is your definition of a nonpolar bond. Alright, so if your bond polarities cancel just like in your tetrahedral very nicely, and then it's going to be a nonpolar molecule, even though your individual bond by itself is considered to be polar. Alright? Well, let's ramp it up a little bit. Let's get rid of this top one and imagine I just have a trigonal pyramidal shape. Alright? So if you look here, what I have now, I'm going to redraw, I'm going to redraw this right here. Here's me. Okay. Here are my 3 Tobys. Okay. Exerting a force downwards, pulling the rope that we were sharing, and now that force is not going to be canceled because there's no opposing force upwards. So this molecule, this trigonal pyramidal, is going to be polar because my bond polarities do not cancel out. Alright? So it's interesting because what you're doing, you're first looking at your bond polarity. So yes, as before, this bond would be polar, but then you have to look at the molecule as a whole and decide if all of the different forces acting on each of the bonds, so this one, that one, and then if I had my other ball that just fell on the ground upwards, okay, those would cancel each other out, making my entire molecule nonpolar. But if you don't have that canceling out effect, then it's considered to be polar.